Hello everyone, True Zero Emissions here. So we have, this is what's called the loving giving path, which is when you charge one battery with another battery. Usually people use lead acid batteries because you can overcharge them. Lithium, these are lithium batteries. We don't want to overcharge lithium. So I have to be very careful to watch the voltage on the battery that's charging to make sure I don't take it over voltage, right? Fully charged is 54.6 volts, so I won't go past that. What I noticed though is that as that battery fills up, this will slow down by itself. It just stops taking energy. That's probably the battery management system causing it to throttle back. I think that's what it's called. I might not be saying that correctly, but it seems to be reducing the power that goes to the battery automatically. I will still monitor it carefully, and I will turn that off once that battery is full. Now, it's supposed to be approximately 10 times more efficient to charge a battery when it's not being used. That's an approximation. That means if I'm pedaling the bicycle, I could have this sending the charge to the battery and charging it, okay? And the load runs for free. We don't lose any energy on the motor. So imagine we're sending power. Let's imagine that electricity in this instance is like water. And imagine that the motor, or whatever this is, whatever the load may be, it could be a light bulb, it could be a motor, it can be a hydrogen water fuel cell, which I've enjoyed putting water fuel cells between two sets of batteries and then charging a battery at the rate of powering that water fuel cell. That's a really fun system. And the power consumption, no, not the power consumption, there's no power consumed. The power that we're charging the battery at the rate of that charge is such a low consumption, such a low, how do I say this? It's such a low number for the hydrogen cell to run. And I'll do some testing on that. I'll do some experimentation on that. Let's see what's happening here. The battery, as you can see, the battery voltage is increasing. This is an 84 volt battery, and this battery is 54 volts. So the way this is hooked up is this big battery is connected to this pulse width modulator motor controller. The output of the motor controller, instead of just going positive and negative to the motor, I have, since I'm using the loving giving path, which you can look up on YouTube, look up Rick Friedrich loving giving path. Rick Friedrich has a YouTube channel. He's a researcher, an experimenter, and he's been studying this his whole life. But again, it's very important to realize that Rick Friedrich doesn't really care about free energy. He cares about your heart. That's the main thing he cares about. So never forget that. If you ever talk to him or want to talk to him, just remember that what he really cares about is the heart, not about free energy. He knows a lot about free energy. He knows a lot about how energy works, but he's not really, what he's really excited about is people's heart, okay? Just know that, it's very important. So the way this is wired is the pulse width modulator motor controller is wired to this high voltage battery, which is a higher voltage than this battery, right? That's required for this circuit to work, because we're sending a charge from one battery to the other battery, right? Now, when we have, on the output of this, there's a positive and negative, right? And I'm going to show you the way it's wired. Okay, so if you look here, I'll just show you how everything's wired. So here's our positive and negative right here for the battery, and that's going to the power of this pulse width modulator motor controller. It's a brushed motor controller, right? This is a brushed motor. Then the output of the pulse width modulator, the negative is going directly to the battery, right? The negative is going directly to the battery right there. It's going to that battery. The positive, this is called splitting the positive. That's one of the ways it's described. If you watch Energy from the Vacuum, which is a free series to watch right now, and I highly recommend watching it. If you just want to spend 15 minutes watching the most important information that everyone says, video 7, the first 15 minutes. Okay, watch that. That's the most important 15 minutes of the whole 42 video series. But the great thing is that the whole series is available for free to watch on YouTube, which is absolutely wonderful. It's highly educational, and I recommend watching it. Yeah. Okay, so going back to the way this is wired. Oh, in Energy from the Vacuum, John Bedini talks about splitting the negative, okay? But Rick Friedrich talks about splitting the positive, and I don't know what the difference is. Maybe it's the same thing, I don't know. Can we split the positive and split the negative at the same time? I also don't know that. That would have to be tested. But in this circuit, the way I'm doing it right now is just the way that Rick Friedrich talks about it, and it's the way that he shows it and the circuits that he has collected, because Rick Friedrich collects information and circuits from throughout history by especially very well-known physicists, electrical engineers, mechanical engineers, people that make things, okay, people that experiment and make things. So on the pulse width modulator output, I think I showed you that the negative is connected directly to the battery, and then the positive, I think that's where I am now, yeah, showing you the positive. The positive is going through the motor, so that's going to the motor positive, and then the negative actually goes to the battery positive. That sounds like series, right? It sounds like I'm going in series. Anyway, that wire, I'm powering this motor with one wire. How is that possible? And some people will say, oh, well, it's a virtual negative. It's a virtual negative. That's fine with me. I like virtual. Whatever you want to call it. Anyway, it's being powered with one wire, a positive. This runs without any loss. This energy is not being consumed by the motor. It's being sent over to that battery. All the energy that's making this motor turn is going to the battery. Every little bit of it. None is lost. Now imagine this. Imagine that this motor, while it's doing that, right, is running a generator. And then we bump the voltage up to the generator, for example, right? Because we can spin the RPMs up, but then I'm going to charge faster if I do that. But imagine we're spinning a generator, and that generator is charging one of these batteries. Which battery would you charge? Would you charge this battery, or would you charge this battery? You know, because this one's being discharged, and a battery does not like to be discharged and charged at the same time, my guess would be that it'd be more efficient to charge the battery it's already being charged. This one's already being charged. Let's charge it more, right? So if this motor was turning a generator, we're turning that generator for free, right? There's no loss because of the way the circuit works, the loving, giving, path circuit. You can research this yourself. Rick Friedrich, in his I'll call them lectures, where you can go and watch, meet Rick in person and see his achievements in his scientific experimentation. Rick took 6 AA batteries, he took, I think it was 12 AA batteries. He wired 6 in series and 6 in parallel, and then connected the circuit the same way I'm doing here, which is, except he didn't use a pulse width modulator, he just connected it directly. He connected the negative of one set to the negative of the other set, and then he connected the positive, he split the positive, and the positive of one set, the positive wire of one set connected to a light bulb, and then on the output on the other connection of the light bulb, it went ahead and connected to the positive of the other set. So that way, in one set of batteries was wired in series, and one set was wired in parallel, and you can keep sending that energy back and forth without loss. There's a little bit of losses when you do it that way, Rick said, so eventually you won't be able to send the energy back and forth anymore, but you can do it like 10 times, which is way more efficient than if we were just using all of those batteries one time. That's very easy to test, and anybody can test that for themselves. It's like, how long would that bulb run for if you were running all 12 of those AA batteries? How long does it run for, and how bright does it run, right? That's a real simple test to do. And then you compare that to running 6 cells in series and 6 cells in parallel, and sending the charge back and forth, back and forth, back and forth. The only thing you change is the batteries that have just been charged, that are in parallel, will be switched into series, and the batteries that were in series that are now drained will be switched into parallel. That way the high voltage will flow back and forth. It'll flow back and forth. It's the voltage. The higher voltage allows that charge to flow. It allows the watt hours or the amp hours or the energy to flow from one set of batteries to the other. Now this is a bunch of batteries in here in series and parallel. This is a bunch of batteries in series and parallel. But the way it's set up is it's kind of sealed. It's already set. So what I'm doing is just taking this battery and using it as a range extender. But I'm experimenting with running a free load. If I say free, I just mean I'm not losing any power by turning this. What's fun about this kind of circuit too is that this is a really simple way of extending the range of something that's electric, but you have to keep an eye on the voltage. You'll have to watch that. See, I'm at 54.1 volts, and I cannot go past 54.6 because that will burn that battery out. It'll damage it. So So what happens is if you have some batteries that you can add in series, you can run them in series to get the voltage higher than, let's say, your electric bike or something, and you want to extend the range, you could run something like this kind of circuit, and that would help extend the range, act as a range extender, right? Because a lot of people want to extend the range of their electric bikes and different things, but you know, this does have a lot of weight to it. This weighs 32 pounds. I weighed it. It's this is 32.2 pounds, and so that does have a significant weight to it. But this is about experimentation, so I'm not really going for the lightest weight right now. I'm just going for what is happening in the circuit, what's everything doing, and how far can I go with that big of a battery, right? See, this is a way of extending the range of my electric bike without changing the battery, the main battery. I'm just adding to it. So what I could do is, like I was saying earlier, I could just pedal when I want to let it charge. I could pedal and then turn this up and let this send the energy from this battery over to this battery, right, at the rate of powering this. So if I wanted to charge faster, I would just turn this up and turn the speed of it up, right? But for now, I'm going to turn this off. We're already at 54.0 volts. I'm going to go ahead and turn this. What I'll do is I'll turn it down. I'm not going to turn it off. I'll let it do a slow charge. And I'm going to let it do that. I'm going to let it send a slow charge over while I'm actually riding the bike, just to see what it'll do, even though I know it's less efficient. The thing is, though, is I'm not always using the accelerator, so it'll charge most efficiently. That battery will charge most efficiently when I'm not accelerating, because when I'm accelerating, I'm drawing power from that battery, and a battery does not like to be charged and discharged at the same time. It's not as efficient. It still can work. It can do it. It can be done. It's just not as efficient as charging a battery when it's when it doesn't have a load on it, right? Okay, everyone, True Zero Emission signing off. We'll see you in the next video.